Hi guys, today I'm going to be talking about some of the formulas for the magnetism unit of AP/IB physics. So the first one we have is the permeability constant, which is also known as mu naught, and it is equal to 4 pi times 10 to the negative 7, and the units for this constant are newtons over ampere squared. Then we have a picture of a magnet. This picture shows how the magnetic field of a magnet leaves the north end and goes towards the south end. Then we move on to the magnetic force, which is equal to QVB, which is also equal to QVB sine theta. Q in this case is the charge, with V being the velocity and B being the magnetic field. In order to calculate this magnetic field, we have a couple of formulas. If we rearrange this equation for the magnetic force, we can get B is equal to the magnetic force over QV, which is just charge times velocity. And the units for this magnetic field are T, which is known as Tesla. Now, if we have a current carrying wire that is a straight wire, then the formula for calculating the magnetic field becomes B is equal to mu naught times I, which is the current, over 2 pi r, with r being the distance from the point which you're calculating the magnetic field at. But if instead we have a circular magnet, like if you have a circular wire, and we're trying to find the magnetic field created by this wire, it becomes mu naught times I over 2 pi. The difference between these two formulas is just that if we have a straight wire, then the magnetic field is calculated with a pi in the denominator. But if we don't have a straight wire, instead we have a circular wire, there is no pi in the denominator. Now, if we're trying to find the magnetic field of a solenoid, we'll use the formula mu naught times n, which is just the number of turns, times I, which again is the current, all over L, or the length of the solenoid. Now, if we're trying to find the force on this current carrying wire, the formula becomes ILB sine theta. In this case, I is the current of the wire, L is the length of that wire, and B is the magnetic field. Now, if we're trying to find the torque of that current carrying wire, I becomes the current, A is the area, and B is the magnetic field. So it's IAB sine theta. Now, in many cases with different problems, we can set certain forces equal to each other. So in this first example here, we have set the electrical force equal to the magnetic force, and the formula is QE, which is charge times the electrical field, equals QVB, which is charge times the velocity times the magnetic field. And then if we simplify this formula, we can get velocity is equal to E, the electrical field, over B, the magnetic field. Now, in this case, for the second example, we have set force centripetal equal to the magnetic force, and then the formula becomes mv squared over r, so this is mass times the velocity square over the radius, which is equal to qvb, which is just charge times the velocity times the magnetic field. And if we simplify this formula, we can get the radius is equal to mv over qb, so that's the radius equals mass times the velocity over the charge times the magnetic field. Now, if we move on and try to find flux, the formula becomes BA cosine theta, with B being the magnetic field, A being the area, and the units for flux are WB or Webers. And now using flux, we can calculate EMF. So the formula for calculating EMF is equal to negative N times delta flux over delta T. And N in this case is the number of turns, and then delta flux is just the change in flux, and delta T is just the change in time. And this formula also equals BVL, which is the magnetic field times the velocity times the length. And this formula also equals NBA W sine WT, which is the number of turns times the magnetic field times the area times the angular velocity. And this is multiplied by the sine of the velocity times time. Now, if we're dealing with a transformer, there's different formulas that we can use to calculate like the number of turns or the current, all the voltage. So we can do this with NS, with S denoting the secondary and P denoting the primary. So NS over NP is equal to VS over VP, which also equals IP over IS. So we can use these ratios to try to figure out any missing things we have.
So there are four different right-hand rules that we will primarily focus on. So the first one is with the palm out, flat hand, and the fingers will point towards the magnetic field, thumb will point towards the velocity, and your palm will point towards the force. keep in mind for the flat hand right hand rules that the force will be swapped, or you could just use your left hand if the charge is negative. So for the second right hand rule, the fingers are going to be the force will be out of your palm, and the thumb will be I this time. For the third right hand rule, you're gonna curl your fingers, so I will be your thumb, and then B will be the direction of the curled fingers. And for the fourth right hand rule, the magnetic field will be up, and then your curled fingers will be the current.
Now, this is one of the common questions that come for this unit all the time. It goes as a circular metal ring is situated above a long straight wire, as shown in the figure. The straight wire has the current flowing to the right, and the current is increasing at a time at a constant rate. Is there an induced current, and what direction is it flowing in? Now, this question utilizes the right-hand rule where the magnetic field is your curled fingers and the current is your thumb. And now, in the problem, if you line up your fingers as it is shown in the problem, the current is facing to the right in the counterclockwise direction. So you point your fingers to the right, and you see where the curled up fingers point towards. Now for me, they're pointing towards my face, so that means that's out of the page. And you can represent this in the diagram by drawing a bunch of dots into the page, or out of the page actually. Now, a good way to remember this is if it's ever represented in paper, any circles, dots, or anything that's something like this means that the force or the vector is going out of the page, and x's represent that it's going into the page. A good way to remember this is to think of an arrow tip, and an arrow tail, as an arrow's point represents a little single point that's going out of the page, and a tail of the arrow has feathers or marks that represent an x. Now, with that being said, it also says that the current is increasing at a time at a constant rate. So that means there's an induced current. That also means that as this current to the right is increasing, the magnetic field at this point is also increasing. And according to Lenz's law, if there's a magnetic field increasing into one direction, in order to maintain equilibrium, there must be a counteracting magnetic field and a counteracting magnetic current going the other way. So if you flip your fingers and your hands in order to counteract the direction of the magnetic field, that would mean that your fingers are going out of the page, that is away from my face. And then you just see which direction your thumb is pointing towards. And in my fingers, if it's going into the page, the current points this way, which is in a clockwise direction. Hence, the answer to this question is that there is an induced current due to the increasing current at a constant rate. And with the right hand rule, you get that it goes to the clockwise direction.
So let's do another question. This question says a proton moves in a circular orbit of radius 65 centimeters perpendicular to a uniform magnetic field of magnitude 0.7 Tesla. So part A asks, what is the period of this motion? So for part A, to find period, we can do T is equal to 2 pi r over V. So we actually have to find V first. So to find V, we can do charge times the magnetic field times radius over the mass. And we know the mass of, or we know the charge of a proton to be 1.6 times 10 to the negative 19. And we get the magnetic field at 0.7, the radius at 0.65 meters. And this is all over the mass of a proton, which is 1.67 times 10 to the negative 27. So doing all this, we get 4.36 times 10 to the negative 7 as our speed. So now we can plug that into this formula right here. So 2 pi 0.65 is our radius. And our speed that we just found was 4.36 times 10 to the negative 7. So we get in total 9.37 times 10 to the negative 8 seconds as our period. And part B asks, what is the speed of the proton? So we actually just calculated that to find part A. So that's 4.36 times 10 to the second negative 7 meters per second. the part C asks, what is the kinetic energy of the proton? So kinetic energy is equal to 1/2 mv squared. So 1/2, the mass of protons to 1.67 times 10 to the negative 27. And then we know the speed to be 4.36 times 10 to the negative 7 squared. And we get that equal to 1.59 times 10 to the negative 12 joules as the kinetic energy. So that's this problem.
Now, this is one of those typical right-hand rule problems that you'll find, and this utilizes a different right-hand rule. This is the one with your palm, where the magnetic field is your fingers, the velocity is your thumb, and the direction of the force is with your palm. And for the so this is with a positively charged particle like a proton, where the palm is the direction of your force. But if you were to be given a problem with an electron or a negatively charged particle, the only thing you change is the direction of the force. So their fingers are still assigned to the same vectors, but the direction of the force is to the back of your hand this time. So for this problem, for letter A, we have the direction of the force to the right, and the velocity going straight down. So if you were to use your thumb as the velocity, and the direction of the force being your palm, that means that the third missing vector, the electric field, is going towards the page. Now, for an electron, it's going to be a little different. So, with an electron, you need the palm of your hand being the opposite direction of the force. So, you would point the back of your hand towards the force and point your thumb down. And while doing that, you get your fingers pointing towards your face. And then that means the missing vector, the magnetic field, is out of the page. For letter B, you have the vectors, your velocity and the magnetic field. So again, for a positively charged particle, you would point your fingers downwards and then point the velocity vector to the right side, and you get your palm facing towards the screen, so that is into the page. And then again, you just flip your palm and fix the direction of your other vectors that are right now, and you get that the force comes out of the page. For part C, you give your thumb the velocity. You give your you put your hand flat with your velocity pointing to the left, and you get that the magnetic field is going out of the page once more. And then again, if you flip your hand and make it so the back of your hand is pointing towards the field force and the velocity vector to the left, you get that the magnetic field is going towards the page. For part D is a special one. Part D and part E. Now, these vectors all have to be perpendicular to each other, and all three dimensions, the x, y, and z. So for part D and E, since they're in the same direction, the magnetic field and the velocity, that means that the third vector is going to be equal to 0. There's no extra force. There's no extra vector. And that's the same for an electron or a proton.